The receiver operating characteristic is a diagnostic tool for describing the quality of two-class classifiers. This talk is going to be a brief description of what ROC curves are and how they work. When building automated classifiers, the engineer will want to be able to quantify performance for his customers and his management. The ROC curve is a tool not only for characterizing performance, but also for intelligently assessing trade-offs. It can be used to quickly decide which of two or more classifiers is better and how to set operating points that are consistent with customer and managerial requirements. Let's start with an example. Suppose you are an intelligence officer who wants to determine if an attack is imminent based on two indicators. Say the amount of fuel delivered to an enemy base and the man hours being worked by the enemy's base staff. We'll call these indicators features. Let's not worry about why we're using these two features or where they come from. Let's just assume we have somehow decided that fuel and man hours are what we want to use. Your operations division sends spies out and collects some data. You find that when an attack is imminent, the two features have values indicated by the circles. When an attack is not imminent, the two features take on values shown by the squares. Building an automated discriminator amounts to picking a curve. When you're given a data point, you report whether the point is on one side or the other of the curve. As we'll see, this can be a complex curve, but for the time being, let's just use this line. If we have a point we think is on the there's going to be an attack side of the curve, we will color it green. Otherwise, we'll color it red. We want the circles to be colored green and the squares to be colored red. We need to evaluate how well this line did, so we can report it to our manager and allow him to justify collecting all this expensive data. We're going to store the numbers for our evaluation in this array. The obvious starting point to creating an evaluation is to count up all the various performance cases. There are 4. We can color a circle green, which correctly identifies an imminent attack. We can color a square red, which correctly identifies that no attack is coming. We can color a square green, which incorrectly declares that an attack is imminent when it's really not. And we can color a circle red, which incorrectly misses an imminent attack. Notice that there are 2 ways of making a mistake, and the potential cost of those 2 different mistakes will be different. If we declare there is going to be an attack when there is none coming, we will mobilize a defense when none is needed. This can reduce readiness, and it will create a sense that our system is a Chicken Little and cause people to lose trust in its predictions. If we miss an attack, we can lose whatever comes of having the enemy catching us unprepared. Depending on the type of attack, this can be a devastating loss. We need to quantify these 2 different kinds of errors. In statistics, these would be called type 1 and type 2 errors, but we're going to do this with machine learning terminology. We want to measure performance. One obvious approach is to take the number of times we get the right answer and divide by the total number of data points. This will give us what's called the accuracy. We'll print that in the lower right of our performance array. The advantage of accuracy is that it's one number between 0 and 1. The disadvantage is that it does not distinguish between the 2 kinds of errors. However, accuracy is popular because there are no trades to think about. It is convenient, but generally not the best way to evaluate a system. Another measure of performance is called the probability of detection. We count the number of times we correctly predict an attack and divide by the total number of attacks. This is the probability we detect an attack given the attack occurs. The probability of detection is also referred to as the recall. We'll write the probability of detection at the bottom of the first column. Notice with the probability of detection, we're only using half the counts. To incorporate the other half, we will take the number of times we incorrectly declare there's going to be an attack and divide by the number of times there is no attack. We call this the probability of false alarm. For completeness, another measure that is commonly used counts up the number of correct predictions of an attack and divides by the number of times we predict an attack. This is called the precision. This is the probability an attack is coming given we said an attack was coming. It is the conditional converse of the probability of detection. Precision is frequently used in recommender systems. It offers a measure of how much you're going to pester someone with wrong answers. The probability of false alarm is often used in situations where you're computing risk more formally. Notice that when you're looking at precision and recall, you're not using all of the counts in the matrix. There's a sense in which you're ignoring some information. It is important to realize that even though we call these things probabilities, They're actually estimates of probabilities. If we collected more data, we'd expect the estimates to get better. We're going to focus on probability of detection and probability of false alarm. We'll want some way to visualize these numbers, and an easy way to do that is to plot them. Now, there will always be two extreme cases for a classifier. In one case, we declare every single instance an imminent attack. The probability of detection and the probability of false alarm are both 1. In this case, we've built a classifier that is a paranoid lunatic. Everything is a potential attack. And this corresponds to the line being shifted to the far negative x. Notice that when we do this shift, the precision is neither 0 nor 1. In this paranoid classifier case, the precision is actually a measure of the fraction of things we're trying to detect in the test set. In recommender systems like document search, you are frequently looking for something rare among a large set of possibilities. So the precision in this paranoid extreme will be small. The other extreme is we simply turn our classifier off. We never declare that an attack is imminent. The probabilities of detection and false alarm are both 0. Our classifier is a pot-smoking hippie who refuses to acknowledge the possibility of anything being a potential attack. This corresponds to the line being moved to the far positive x. It is natural to wonder what happens between the two extremes of a peacenik focusing positive energy into New Age power crystals and a jaw-clenched lunatic who will do anything to preserve the purity of our bodily fluids. We can see the middle ground by sweeping the line from positive to negative x. If we do the sweep and connect up the measurements with probability of detection on the y-axis and probability of false alarm on the x-axis, we'll get a curve. This is the ROC curve for the line classifier as its position is varied from positive x to negative x. It is a map of the performance between those two extremes. Before talking theory, let's review some history. We call these curves receiver operating characteristics. That's a pretty specific and technical sounding name. Where does it come from? The early days of radar were military projects. Transmitters and receivers were expensive installations. The problems they were trying to solve were very much like our example. The operators would send out a pulse, and if something like an airplane or a ship was present to reflect the pulse, they received a return. The return, however, would be noisy, so there's a problem with determining if something is present or if they're seeing a randomly large spike. We'll mark the locations where there is nothing with squares and location where there's a return with circles. Now, instead of 2 features like a previous example, there is only 1. But it's hard to see on a single axis, so we'll spread it out on the x-axis. Defining a threshold that determines if a return is present amounts to selecting a line parallel to the x-axis. Let's sweep these lines out. This produces a receiver operating characteristic curve, a curve that characterizes our radar receiver. If we do this for a radar receiver that is somehow different, maybe a different antenna, we will get a different ROC curve. An ideal ROC curve will have at least one setting where the probability of detection is 1 and the probability of false alarm is 0. This is the upper left corner of the graph. It stands to reason that a curve that most closely approaches that condition represents a better system. By comparing the ROC curves, it becomes clear which radar setup is better. The curve that is more bunched in the upper left corner is a better system. Let's look at a little theory. In particular, we'll discuss area under the ROC curve. In the history discussion, we made a decision by comparing a number selected from one of 2 clusters. As we'll see, this is almost always the case when making a final decision in a classifier with 2 categories. It is natural to think of these clusters in terms of probability distributions. If we further assume the distributions are Gaussian, we can derive formulas for the ROC and its properties. Given 2 single-value distributions where thing we're looking for comes from the more positive distribution, if the number we see is bigger than a threshold, we say we found thing. Otherwise, we say we didn't find thing. In our example, thing has been an imminent attack. The probability of detection is the area under the green curve to the right of the threshold. The probability of false alarm is the area under the red curve to the right of the threshold. When you pick a threshold, you pick a point on the ROC curve. If you sweep the threshold, you sweep out the ROC curve. Our system is good when 2 distributions are easily distinguished. In this case, the ROC curve gets bunched in the upper left. Our system is bad when the 2 distributions cannot be distinguished. In this case, the ROC curve is a line from 0, 0 to 1, 1. As a side note, you might think the ROC curve dipping below the line is even worse. But all that means is that we've moved from large numbers being an indicator of what we're trying to detect to small numbers being an indicator of what we're trying to detect. The green curve is moved to the left of the red curve. Since we often want a single number to define quality, it is common to use area under the ROC curve. This will be a number between 1/2 for terrible to 1 for best possible. If we assume the distributions are Gaussian, it is possible to derive a formula for the area under the ROC in terms of the means and variances of the two distributions. We can further use this formula to derive standard error for the area under the ROC, which in turn can give information about the number of data points required to draw conclusions, whether or not we're overtraining, or when we should think an ROC curve with larger area is truly better. This is an application of calculus and statistics, and I might do it in a future video if I think there's interest. Before evaluating classifiers on our original example, let's talk about how we'll construct ROC curves with a modern classifier. So far, we've been creating the ROC by sweeping a line. This is generally not going to be feasible with a modern classifier. Classifiers generally produce what could be called probabilities given input. Whether or not we should really think of them as probabilities is a philosophical question. Ultimately, you have to make a decision based on these probabilities. You could just choose the larger probability. On the other hand, there's no reason to think that the training algorithm picked the very best operating point for a policy not represented in the training data. It is common to simply take the ratio of probabilities and compare to a threshold. There are theoretical reasons, like the Neyman-Pearson lemma, why this is a good thing to do. This threshold is what we sweep to construct the ROC curve. Let's look at logistic regression. Because of how vanilla logistic regression works, the curve is still simply a sweeping line. Now consider a neural net. The piecewise linear separating function is characteristic of a multi-layer perceptron. How about support vector machines? Using the kernel trick creates curves that have different topologies. For a random forest, the implicit function plotter didn't work so well, so I'm not plotting the separating curve. Finally, we can remap the features from xy to x, y, x squared, y squared, and so on, and use logistic regression. Like the SVM, this produces a separating curve with varying topology. Collating all the ROC curves, we see that using remapped feature logistic regression is the winner. This means that logistic regression is all you'll ever need for building any classifier ever. If you have any comments, please leave them below, and thank you for your attention.